The electric fields due to continuous charge distributions. In the dipole calculation, we dealt with discrete charges. If the separation between the charges is infinitesimal, then the charge distribution is continuous. To sum these infinitesimal dE fields due to dQ, it requires integration. So if we deal with discrete charges, then we write dE net is then going to equal to the sum of all of the electric fields, where each field is then given by 4 pi epsilon Ri squared Qi in the direction of Ri. But if I have a continuous charge, then our dE net field or E net field is now integrating all of these little dE fields, where dE plays the same role as before. So the process for solving for the electric field with continuous charge distributions is, one, you have to determine how much charge EQ is there. Two, we have to determine the displacement vector. Now, when I'm looking at this thing here, note that the only thing that's really new here is that this is the charge element dq. We always calculate the displacement vector if we have to calculate an electric force or an electric field. So now if I put this all together, we finally get our little dE field. So when I say dE field, you're going to find here is that we're going to need the magnitude. And it's more common to calculate what is called the directional. So the magnitude is then going to be this 4 pi epsilon r squared over dq. Now, typically we've said the direction was the angle theta, but you're going to see that that's typically not most useful. What's most useful is the directional or the cosine or sine functions or whatever combination that we need. So we need those two things, and that all comes from the displacement vector. And then finally, we then integrate over all the little dE's. In other words, we're going to take E and we're going to integrate all of them, which just means that I'm integrating over 4 pi epsilon r squared dq. And then I'll have some directional that I'll most likely have to apply. So the first thing, if you look at that step one, is how much charge is dq. So the first thing that we got to do here is that we need to determine the amount of charge dq. To determine the amount of charge dq located at some position contained in some geometric volume. Now that could be a linear volume, that could be a surface volume, or that could be a volume. So to determine the amount of charge that's in there, we need the charge density function. So mathematically, it describes how the charges are distributed. As a function of position. So there's three types. There's linear, surface, and volume. So let's start with the linear charge density, which is defined as lambda of x. So let's look at the definition. So the definition is that we have a linear charge density, and that is going to equal to the total charge divided by the total length. So lambda is equal to total charge divided by the total length. So this is the way it is typically defined right here. And then unit-wise, we see that a unit of linear charge density will be a unit of charge over a unit of length. So this becomes a coulomb per meter. The most common type of charge density is constant. That is, the charge is uniformly distributed. So for a linear line, that means here is that I'm going to have, let's say I have this size length of line. And then if I break them into little tiny units here, I'm going to put a tiny bit of charge in each of these units. And in this case, we'll say that the length here is L. Now, we can see here that this is 1 square, and that's going to be our length. And so when you're looking at the total length of this thing, 1, 2, 3, 4, 5, you can see that the total length is 5 squares. So what does lambda equal to a constant mean numerically? So we want to calculate two things here. So the first thing we want to look at is we want to look at the charge density for the whole line. So in this case, we then say that lambda for the whole line then tells us what's the total charge divided by the total length here. And in this case, you could see that if I have 5 squares and I have 2 charges per square, that's going to give me a total of 10 charges. And that's going to be over 5 squares. In other words, my charge density is 2 charges per square. We could have looked and we could have said that. But the other thing that we can do is that we can look at the charge density of a smaller length. And in this situation, what if I pick just one charge unit? So if I pick one charge unit, so I'm going to pick a little q and I'm going to pick a smaller distance. So for one charge unit, I could see here is that I contain one charge, and you could see that it's only in half a square, which then gives me 2 charges per square. That's what I mean by a constant charge density. So when we write lambda is equal to a constant, it is over the total length into the total charge, or I can take an infinitesimal amount. Which then allows us to define dq, which is lambda dx, and this is what we call the charge element. And that tells us that that amount of charge dq is contained within a linear volume of dx. So now that we've done that, I'll move quicker through the other charge densities. I'm going to have a surface charge density. And this here is defined as eta of x of y. So the fact that it depends on x or y tells you that it's a two-dimensional charge density. So then we play the same game as before. The definition is that I have a surface charge density which is equal to the total charge over the total area. So in other words, we could set eta equal to the total charge over the total area. But now, as okay, let's leave it like that. And again, unit-wise, it's going to be a unit of charge divided by a unit of area, which will then be coulombs per meter squared. So if we have a uniformly charged surface, then eta is either the total charge. Let me be careful here. So if this is a constant, then this will be the total charge over the total area, will also be some infinitesimal charge distributed into some infinitesimal area. So if I think about this picture-wise, I could imagine that I have a surface that looks like this. So now what I'm going to do is that I'm going to compartmentalize the charges. Assuming that these are all equally spaced, which clearly I've drawn that these guys are not equally spaced. So then each little unit has a charge that looks something like this. So clearly that's a surface right there. And so if this is a plane, I can define this as x. I could define this as y. And that's going to give me my area. So then if I look at for the whole surface area, we would then come in here and say that, okay, now eta is then going to be equal to big Q over the total area. But if I'm looking at just an infinitesimal amount, so if I come in here, let's say that I look at this guy right here, I know that this guy contains a little bit of dq here. So when I look at this guy, I could say that this would be eta of dq over dA. So then if I look at in infinitesimal area, I could then define lambda as dq over dA, or I can write dq as as lambda dA. So for a volume charge, it plays the same role. But in this chapter, we're not going to deal with volume charges. We're going to deal with them in the next chapter. So here I'm just going to summarize it very quickly because it follows the same path as here. So then we're going to have a volume charge density, which is defined as rho, which is now x, y, z. And so if I look at the charge density, we could then come in here and we could say this here, so that the volume charge density, which we've defined as the charge density rho, if this guy is a constant, then we can come in here and write that the total charge over the total volume is also the infinitesimal dV. Again, if I look at my units, I could say that a unit of rho is equal to a unit of charge, unit of volume, which will then be coulombs per meters cubed. So just picture-wise, we would then draw a cube, for example, to make it easier. So in my picture, I could imagine that I have a little cube. And then I just partition this guy. And so if you're looking at these partitions, I can come in here and I can put a uniform charge in each of these little cubes. I don't have to put positives everywhere, but there you are. So if I look at this, the thing that we want to focus on is that if I look at one little tiny cube right here, that little cube right there is going to tell us that I can rewrite this as dq, and that's going to be the charge density times the volume. So if I look at this, there's one other charge distribution that we should think about. So if the charge distribution is not uniform, one has to parameterize the charge density as a function of position. One example would be is that if I have a line charge like this, then I could have, I don't know, charges that do this. And then that means I have to come in here and I have to write a function of lambda, which is a function of position. And so once I do that, then we can define the total charge, which then says starting with this guy, we could integrate over all of the charges which then gives me lambda of x dx. So to finish up the section here, to compute the electric fields of a continuous charge, I will follow this outline for problem solving. I'm going to start with step 1. And here I ask the question, what is the physics of the field before you calculate it? Step 2, define the charge element dq. Then we just follow the steps that we've already gone through. And then step 3, we calculate the displacement vector along with the little electric field dE, where dE is then going to be 4 pi epsilon divided into dq r squared r hat. Then I need to finally integrate this function. So I'm going to integrate over all the dE fields. So in other words, I'm going to have E will be the integral of dE. And then finally, we need to check our results. Does this mathematical solution of the field equation agree with our initial assessment from step one.